Orion Ning is a third-year graduate student in the Berkeley Center for Theoretical Physics in the physics department. He works on problems related to the particle theory of dark matter and how we might be able to detect signatures of dark matter candidates using techniques in astrophysics. Take it away.
Yeah, thanks for the introduction, and thanks for having me. Right, I'm a graduate student in the Berkeley Center for Theoretical Physics, and basically a lot of my specialty is in this thing called dark matter. Um, so uh, I appreciate the opportunity to basically tell the story of dark matter today and kind of why I find this problem particularly compelling and particularly interesting, especially in the next decade or so. So I call this the cosmic game of hide and seek, chasing dark matter across the stars. We're going to be covering a lot of different topics now because the dark matter problem has become increasingly interdisciplinary. I'm going to first get started by saying, let me see. So what have you heard about dark matter? And so it's difficult for me to see if there's anyone in the chat that says anything, but at the undergraduate level, you probably have heard a little more about dark matter than just say like the average person on the street. Is there anyone in the chat? Otherwise, that's also completely fine. Sounds good. Yeah. And so every time I have a question mark on here, it's and it's kind of a question to the audience, but also they can also ask me questions at any time. But otherwise, I'll just keep going. Yeah, I feel like this is a thing that's kind of briefly mentioned perhaps in some undergraduate classes. And my audience is mostly undergraduates, right? Maybe this story isn't so clear, or maybe like the kind of dark matter research, I'd say, isn't so clear to many of you in the audience. So let me first contextualize the problem. What's the actual status of like dark matter research, but more broadly, particle physics research at large? And so here I've kind of put a couple of news articles that basically discuss this thing called the P5, which is essentially some government advisory panel in which a bunch of physicists get together and they make recommendations about what are the most promising directions forward in particle physics. Funny enough, actually, a member of this committee is actually Hitoshi Murayama here at Berkeley, and I think he was actually a Compass speaker not too long ago. But he and Berkeley in general has a large role to play in determining what is the path forward for particle physics in the next decade. And this is also like a period of deep reflection too for the community, because it makes you wonder, what are the actual problems that we might be able to solve? How might we actually go out and solve them? Kind of what things should we prioritize as a community of physicists, both theorists and experimentalists, moving forward? And if you actually go into the P5 report, they kind of have a list of like recommendations, very broad recommendations for kind of what they think are the most promising directions in particle physics. I kind of want to highlight two of them because they'll be directly related to the topic of my talk. One is like the search for direct evidence of new particles, and then two is determine the nature of dark matter. And that's really going to be the focus of my talk, is kind of how this question of dark matter is now kind of in the focus of particle physicists these days. And I'll talk a little about why, and then kind of this entire grand kind of idea of looking for evidence of new particles that will answer questions that we haven't been able to answer for the past few decades or longer. Again, this is also like a period of deep reflection for the community. So here I kind of pull two quanta articles that are a little pessimistic in the sense that they detail essentially failed searches for a lot of theories that people thought they believed in, such as supersymmetry. And I'd say, that some might agree that the Large Hadron Collider and the discovery of the Higgs boson in 2012 was probably the last like major discovery in particle physics. And ever since then, we haven't really been able to, in my opinion, arguably make very much progress. And so the question you might naturally ask, and the question that a lot of particle physicists ask is, have we kind of hit a roadblock? we can only probe such high energies. There are like future colliders that are being proposed that can also kind of push the boundaries of this, but what kind of new physics is really out there? Because a lot of it, for example, might really be untestable with technology that we'll have now and in the near future. And so this is a big question that people have to grapple with. Maybe we won't be able to find new physics in any reasonable timeline. Although today I kind of want to tell you that, in my opinion, dark matter may be the next new physics. And so what I mean by this is I think dark matter will be one of the most promising paths forward in terms of the particle physics searches in the next few decades. And throughout this talk, I kind of want to give an idea of why. The overview is that I think one of the most important, we know that dark matter must exist. And this is a very non-trivial statement, but dark matter actually is a very tangible thing in the sense that we have a lot of evidence for it that affects things on astrophysical scales. And so this is like a real problem that we don't know how to explain. And so we have a little bit of a handle on this. Because of kind of this evidence that we have, we can infer many of its properties. And so that already tells us a lot about dark matter and makes it a bit more concrete, I think, and more tractable than perhaps a lot of other problems in theoretical physics. The next thing is we have many motivated theories to test, and I hope to go over some of these theories today. But there's a lot of theory that people have about like these new particles that might make up dark matter, and they solve a lot of different types of problems. And so it'd be kind of exciting to see whether this is a particle that actually would solve a lot of these problems in physics, including dark matter. And so we should go out and look for them. And then finally, we are in the middle of a golden age of data. And I think this is often a very underappreciated point, but it's very important. It means that we can actually go out and look for, dark matter evidence in the data sets that we have, which are collecting more and more, accumulating more and more, which allows you to probe more and more sensitive couplings and interactions that dark matter might have. And so I hope to kind of illustrate that dark matter kind of has a legendary past. I think it's a very interesting story how we came to this idea in the first place. A very busy present of like people and researchers who are kind of working on the dark matter problem, and an exciting future, which gives it a sense of renewed optimism in the 21st century. And this is why I think the dark matter problem is particularly special and particularly interesting, particularly if you want to look for something and actually discover physics in your lifetime. So the roadmap that we're going to go is kind of divided into three sections. One is astrophysics. What do we actually know? How do we come to this idea that there's this thing called dark matter? And now that we have that, the natural next question you ask is, what can it actually be at like the microscopic quantum level? We like to describe our world as like particles. And so what could this dark matter particle possibly be? And then three is what I call science. It's the thing that we actually do to go and quantify and make discoveries, is how do we actually go and look for these types of particles? And I'm going to put a little subsection here, which I'm going to say is reminiscent of the title of this talk, which is Among the Stars, ? In the sense that this is kind of what I do. I'm going to talk a little bit about what I do, which is looking for dark matter back in astrophysical data sets, as well as how it might show up at the theoretical level in a lot of astrophysical environments. And I find this particularly exciting, and I hope to show you why. So the first thing that we're going to talk about is the astrophysics. So what do we actually know about dark matter? Well, the first thing that, perhaps some of you have listened to a bunch of these compass talks before. There was probably some overlap with some people who were talking about, for example, dark matter in some other contexts. They might have talked about, for example, the classic story of rotation curves. Today, I kind of want to talk about something a little bit different. I'm going to start with probably what the first kind of hint of dark matter was, which I claim is going to be the thinking about the coma cluster by Fritz Zwicky in 1933. So here is an image of a coma cluster. The coma cluster is a collection of like thousands and thousands of galaxies that are bound together gravitationally. So Zwicky kind of had this idea. He was a Swiss astronomer. He had this idea that you could look at this cluster, and this can tell you a lot about the like how, by looking at like the individual galaxies in these clusters, you can tell a lot about how this galaxy came to be formed. The natural question he asked is, here's one thing I can actually go out and measure with my, by today's standards, probably somewhat primitive telescopes, is how do galaxy speeds play a role? I can measure a galaxy speed, but what will that tell me about the galaxy? And so the kind of natural conclusion he got, which I think makes intuitive sense to all of us, is that slow galaxies tend to be captured by gravity, right? And I think this naturally makes sense. If you're kind of slow moving, you don't really have energy to kind of escape the confines of the gravitational bound of all these galaxies together, which is what a fast galaxy would do, right? If you have a fast moving galaxy, it's going to fly away from the cluster. And so then he realized, well, if I can measure the galaxy speeds, then that can tell me essentially how massive this cluster is. The Coma cluster is a bound cluster. All these galaxies are bound together. And so the thing that he was really hoping for was that by measuring the speed of like the fastest moving cluster that's still bound, I can infer a mass of this cluster that is able to still keep these fast moving galaxies bound together gravitationally. Of course, this is where the kind of dark matter problem arose, is because he found that in order for this mass that he inferred from galaxy speeds to actually be real in the Coma cluster, this couldn't come from just the starlight that you look at in these galaxies. And so there's some unaccounted for dark mass. And so he actually first coined the term dark matter in German in his German paper, Dunkelmaterie. And this is kind of, to my knowledge, the first mention of someone actually proposing that there was this unaccounted for mass that we didn't really know how to explain. Of course, that wasn't the end of the story, right? People were skeptical of this since 1933. But slowly over the rest of the 20th century, we've accumulated a lot more astrophysical evidence of dark matter. Like rotation curves might be a story that some people know about, where if you just look at starlight, you'd expect stars near the outer edge of galaxies to move a lot slower than stars in the inner edge, but actually they move at the same speed, which means there's some mass that's missing that's helping them gravitationally. People also point out to things like the Bullet cluster, which is two clusters of galaxies that are moving into each other, and you can track essentially where all the mass of the galaxy is moving, as well as the gas. The gas has this friction that makes it kind of that makes it like collide with itself, and then the rest of the mass, which would be dark matter, is actually moving like as if there was no interactions at all. This is another popular thing people like to bring up about dark matter searches. The Coma cluster is the story I just mentioned. Gravitational lensing is kind of another interesting thing people have thought about, where you can have maybe some mass that is unable to be observed, but it does leave a signature in having a gravitational effect on light that passes through it or passes around it. It can bend light. Structure formation is another interesting one people study and kind of deduce that dark matter is actually necessary in order to provide the structures of galaxies and galaxy clusters in our early universe. Otherwise, things would not have enough mass to actually coalesce into galaxies in the early universe. And then we have the cosmic microwave background, where dark matter can also leave imprints on the early power spectra that you might get from looking at like early universe signatures of this of all the components that make up the early universe. And so this is not a non-exhaustive list, but all these things kind of accumulate together and really convince people that dark matter is a real phenomenon that must be present in our universe in order for us to exist. And we have no idea really what it is. But we do know, we can infer that dark matter makes up like 84% of all matter that we know of, which is the majority. And it's very, very puzzling that we still really have no idea on what this kind of mysterious thing is in our universe that's causing all of these effects that we really cannot explain. And so that is the dark matter problem in a nutshell. And kind of the approach that I like to think about, and people in my community like to think about, is that you started with astrophysical evidence of dark matter, and I think it naturally makes sense to start to look for astrophysical evidence of dark matter particles. So you come back to the astrophysical stage and look for a more precise study of what dark matter can possibly be at the particle level. This will kind of be the focus of the latter half of my talk. But before we can get to particles, now that we mentioned particles, I kind of want to go into the next section. Before any of this, though, anyone have any questions about the astrophysics? Okay, we're good. So then now we'll kind of go into what I think is the next really fun pillar of this entire study, which is the particle physics. What can it actually be? And I kind of liken this to wanting to know what's inside like a Christmas present without actually being able to open what it is, right? So let's say, Santa comes down and gives you a Christmas present under your tree, and you being the naughty kid that you are, you want to really know what's in this present before Christmas Day. So you go downstairs and you look at the wonderful gift that Santa has presented you. It's this black box. So you can't open it though, or you'll incur the wrath of Santa and perhaps your parents. But you really, really want to know what's inside this thing that you cannot open. So what are things that you can do to it? You can hold it, right? You can kind of shake it around, see if it makes noise inside. You can weigh it. You can put it on a scale to see how big it is. You can put like a magnet against it or something to see if it's like, for example, magnetic. And these are basically all the same tricks that a lot of like particle physicists do because we have this box that's called dark matter and we don't know what kind of a particle it is, assuming it is a particle. And so this is kind of the games that we have to play. We have to see what kind of properties this must have by trying to do all these experiments, do all these observations, and do a lot of theory to kind of see what about dark matter we can probe. So I'm going to talk about kind of where we are in particle physics and this is kind of the baseline to see, what kind of a particle dark matter would be. We encapsulate all of our knowledge of particle physics into this thing called the Standard Model. The Standard Model is essentially our encyclopedia of all particles, fundamental particles that cannot be reduced even further of things that we know of in nature. And so, there's a lot of particles you probably have heard of already. Here is, for example, an example table of the Standard Model that you can find on like Wikipedia or something that kind of lists, these are like the particles that we think are like the most fundamental and the ones that we have been able to discover and verify so far. If you have taken, for example, quantum field theory, which is kind of the language that we use to talk about particle physics as like particles arising from essentially vibrations and fields, particle fields that permeate the universe. You can also encapsulate the entire Standard Model into mathematical form. This is kind of what people do at the research level is they kind of look for these, they play around with the math, they play around with the physics to look for like, properties and interesting things that you can do with these types of particles. But kind of as an overview, high level, let's kind of go over intuitively, physically, what do these particles actually mean? So, perhaps kind of the thing that you might have learned of in like, when you were younger, is there's this thing called the atom, right? The atom is, I think, the smallest unit that's probably taught up to like high school or something like that. And the atom is made up of like several things that you're probably familiar with. One is, of course, like the electron. I think the electron is the most familiar to most people. It's the thing that powers like circuits and things like that. But the electron are like usually represented as like these negatively charged things that kind of orbit the atom in a very broad sense. The electron also has some heavier cousins like the muon and the tau, which actually have very similar properties to the electron, but they're much heavier. And then you can ask, well, what about the nucleus? We have things like protons and neutrons, right? But as it turns out, we've discovered that the protons and neutrons are not the most fundamental. They're actually composite particles made up of these smaller things called quarks. And these quarks are kind of fun. They're called like up, down, charm, strange, top, bottom. These are kind of the ones that we've discovered. And these quarks basically come together, glued together by these things called gluons, to form the essentially like nuclei that you might be more familiar with, like protons and neutrons. Like a proton is two up quarks and a down quark, and a neutron is like two down quarks and up quarks being fused together in like this very in the sea of like other types of quarks and gluons together. And so like nuclear, like this kind of all this like nuclear talk and talk of like quarks and gluons kind of fall into this thing called quantum chromodynamics, which is kind of an infamously difficult thing to actually like calculate and probe. But people have been making progress in it, and basically, I think we can reasonably say at least physically we kind of understand the quarks and the gluons relatively well, at least at the physical level. Here's like a fan favorite. We have the photon. So the photon is basically, excitations of like the E&M field, and it's responsible for things you're probably very familiar, like light. So I think the photon is probably familiar to many people. Then you kind of have these other ones that, perhaps your person on the street really wouldn't have any idea about or really wouldn't care. But I think these are very interesting in their own right. You have neutrinos, kind of one of these kind of mysterious particles that are still a very hot topic in like physics research today. There's extremely light. They don't have any charge, and they all have like this thing called flavor. So you can have like an electron, a neutrino that's flavored like electron or like a muon or a tau neutrino. Um, and these kind of interact with all the other fermions, which are on the left side, like all the quarks and electrons and things like that, interacting with these gauge bosons called the Z boson and the W bosons in this thing called the weak force. And the weak force is kind of one of these special forces that allows you to kind of change particles into each other. It's the only force that really allows you to do this, as well as being responsible, maybe in a more mundane sense, to things like like nuclear decay and nuclear processes. And that's probably why your average person on the street doesn't probably know very much about the weak force, because it's not as famous as like light, for example, but it is very important in our theory of the Standard Model. And kind of the last one on the right there is this thing called the Higgs boson, which was very theoretical up until 2012. I represent it as a picture of an elephant because it is the common paradigm is that the Higgs boson are excitations of this underlying thing called the Higgs field, and is the Higgs field in this kind of beautiful story of spontaneous symmetry breaking that maybe Hitoshi or some others have mentioned in like a previous Compass lecture, that allows the Higgs field to couple to a lot of these other particles that basically provides a mechanism for them to gain mass, uniquely gain mass. So the reason why a lot of these particles, like the electron, the muon, the tau, the quarks, they have mass is because of their coupling to the Higgs field. And this was a very theoretical thing for many decades. But in 2012, the Large Hadron Collider, right, which is this giant facility under the border of Switzerland and France, particle collider, actually discovered the Higgs boson in 2012. And they found evidence that the Higgs boson really did exist. And this was like a beautiful moment in physics. If you go to CERN, which is the facility, kind of the facility organization that houses the Large Hadron Collider, they have like this shelf where they have just a bunch of like champagne that was from essentially when they discovered the Higgs boson in 2012. And so this was a big deal in physics. But that's really the last thing that we kind of discovered in a major sense in particle physics. Now you might ask, like, where is dark matter in this model? It's a rhetorical question. The Standard Model can't explain what we observe from dark matter. And so now we're kind of very puzzled, right? So the people who really believed in the Standard Model now have to acknowledge the fact that dark matter, as well as many other problems, cannot be explained through the Standard Model. So your things like rotation curves, your things like the bullet cluster observations, none of these types of particles would really have the right properties to be a dark matter candidate. As an example, right? Maybe you just wonder the most naive thing: why can't an electron be a dark matter particle? Well, because the electron is charged, right? So if a dark matter was charged, you see a lot more interactions on like the electromagnetic scale, and there would be a lot of different types of evidence that you would have already seen in looking at these like galaxy observations. And so basically it can't be something that's charged. Well, what about like a neutrino or something? Neutrinos for a long time have been a very popular candidate for dark matter. But people have basically decided neutrinos really can't, because in the early universe, neutrinos, because they're so light and they're so small, they stream too fast. And so they would actually wash out structures that you really hoped you would get, that is responsible for like forming early galaxies and galaxy clusters. So this is why neutrinos have kind of been ruled out, is because they move too fast. And so we don't really know exactly what dark matter can be. And so now some might, say this is not where you should be sad. You should be happy, because this is kind of where the fun part is. What can like theorists now actually come up with? Like the whole playing field is open, right? The natural question that I usually ask is, what do most physicists think? Like, how do you even come up with like a new particle? And I'm going to bring up this diagram, which I really like, which is from a person named Karen O'Hare, who's very active in the dark matter community. But it's essentially like a broad picture of what possible masses dark matter could have as a fundamental particle. And so, maybe one question I can ask the audience is, for example, why would where would you think that dark matter might lie on this plot? What kind of a mass would a dark matter particle might lie on this plot, and why? Yeah, it's a little bit of a kind of a silly question, right? Because you have no idea, and I think that's kind of the point too, right? Because nobody really has any idea, and so it can be as small as like 10 to the minus 21, EV, to something as large as maybe like 10 to the 27 EV or so. And just to give you kind of a sense of scale, um, uh, the difference between like 10 to the minus 9 EV and like 10 to the 15 EV is like the difference between a drop of water and the water in all the oceans of the world. And so this is like a huge difference. And now you're talking about like a fundamental particle, which can have like such a huge difference in mass, kind of goes to show our ignorance in what dark matter really can be. And so, of course, these types of different dark matter candidates would have very, very different properties. But I think just basically the idea is we really have no idea. But that means that you can start making your models. And you can start doing a lot of very interesting physics with these types of models. And by the way, an EV, for those not familiar, is kind of a sense. It's probably most familiar to people as like an energy scale. It's formally the amount of energy an electron picks up as it goes through 1 volt. But in particle physics, we often relate energy and mass together because from like Einstein's equations, like E equals mc squared, for example, something that has some characteristic energy also has a characteristic mass. This is the idea behind, for example, like the atomic bomb, right? And so we often talk about like masses of particles in terms of this unit EV, which is very convenient for like subatomic particles. So let's start on the kind of dissecting this plot a little bit. This chart, we have kind of masses that maybe some people are more familiar with, like normal people are more familiar with. For example, something that's like 10 to the 30 EV in mass is about like the mass of a mosquito. Maybe that's a good like baseline point for humans who are based in reality. And if you can go down a little bit further, maybe like 10 to the 24 EV or so, and that start to get to the mass of like a cell, which is like around a nanogram. And then you can go down maybe the 10 to the 21 EV, and that's about like the mass of a DNA strand. And so this is kind of all the stuff that, maybe we're used to at the human scale. Smallest things we're used to at the human scale. But of course, our fundamental particles are fundamental. They're even smaller. And so here are essentially the standard model particles. You have like your fan favorite, like the electron, which is at the middle of this diagram, which sits at around half an MeV, or like 10 to the 6 EV. And slightly heavier are like these quarks. The muon is also slightly heavier. At the very top, you have things like the Higgs boson, which is like 125 GeV, as well as the top quark, which is even heavier than that. And then you have on the left, these neutrinos. And now these neutrinos are represented as these lines because we don't really know what the mass of a neutrino is. For a long time, it was thought that neutrinos are actually massless. But it turns out, neutrinos actually do have to have some kind of non-zero mass, but we don't really know what that mass is. And they seem to be extremely, extremely light, probably below like an EV or so. And so this is kind of where our standard model particles are situated within this entire length scale. And so the question is, where could dark matter be? Right? Where would we actually look for dark matter? How, do you want something that's kind of close to these standard model particles? You want something that's even bigger, even smaller? And for theorists, the playing field, again, is all open. So people have looked all over the scale, and people have come up with theories all over the scale for like different particle candidates for dark matter. And here some of them have like are kind of interesting to think about, like axions. I'm going to talk about axions in a little bit. There's like WIMPs, weakly interacting massive particles, which I'll also talk about in a little bit, which are on the heavier side. And like even more extreme things than these that some people think might be like a dark matter, might actually be like a dark matter particle candidate. And so I also, this plot is also divided into like a wave-like and a particle-like side, in the sense that like below a certain mass or below a certain energy, you're better off characterizing your dark matter particle as something that's kind of akin to a wave, like a light wave or something, because it behaves a lot more like that. This is in the case of like a very light axion-like particle, for example. And something that's more particle-like is kind of a bit more heavy. It's able to be localized more. And so you can treat that more as like a particle. But these are just descriptions of, fundamental particles, which will have a role to play in how you might actually go and detect it, for example. So I also kind of likened the previous chart to kind of a map of a zoo, right? Like all these different dark matter candidates are like different zoo animals. They're very different. They can be very different in more ways than just their mass. And a lot of them can come from completely different theories. And so now the question is, as we're going through this zoo, which of these animals is like a dark matter candidate? And so I'm going to kind of go over like the three in my opinion, the most interesting or motivated ones that, are probably the most popular that people are familiar with within the dark matter literature. Exhibit A is kind of WIMPs, a weakly interacting massive particle. So a WIMP is kind of a it's a very generic particle, and it's one of the first that was proposed in the 70s and 80s. The name kind of says it all. It interacts very weakly to the rest of the standard model, but it does have mass, and that allows it to interact very strongly with gravity. Um, there's a lot of different types of models you can make within the WIMP space, and a lot of them can like self-annihilate. So you can have a WIMP annihilate with itself. So in the bottom left plot, for example, if WIMP is dark matter, you can have it annihilate into itself and produce a lot of signatures of standard model particles we might observe. People, for example, have looked for like WIMP annihilation in the galactic center, and where there's supposed to be a lot of dark matter together, and if they annihilate, they should create like a very bright signal of particles. Um, and this is very appealing for cosmology and supersymmetry reasons. There's this thing that some of you might have heard about called like the WIMP miracle, which is essentially just a statement that like if WIMPs compose or the dark matter candidate, you can have WIMPs in the early universe in thermal equilibrium with like the rest of the standard model, and then they would basically freeze out after the universe has cooled for a while into the dark matter abundance today. The cross section that WIMP must have in order to get the right dark matter abundance today is actually the same that was predicted from supersymmetric extensions of the standard model for a generic WIMP particle. And so people get very excited about this because coincidences are definitely worth a lot of study in theoretical physics. So people like it for all sorts of reasons, right? And like supersymmetry, by the way, is kind of an extension of the standard model. There's like this cartoon on the top right, which basically says that like these supersymmetric particles we haven't observed yet that are like counterparts, counterpart particles to every particle that we know of in the standard model. Although we really haven't found like evidence of this in like the LHC, even though people have hoped we would. It's still a theory that a lot of people think about. So the Higgs-Zeno, for example, is kind of one of the famous WIMPs that are out there that people think still might actually be the dark matter candidate. It's kind of a like super partner of the Higgs in a sense. And people do all sorts of things looking for these Higgs-Zenos in like astrophysical environments, for example. And this would be kind of on the more heavy side of the dark matter plot and on the lower right, where WIMPs would occupy maybe around like many GeV to like a TeV type particle, which would be like amongst the very heavy side of like the particles that we know of. Exhibit B are these things called sterile neutrinos. So a lot of people like to think about sterile neutrinos. They're a heavy counterpart to the ultralight active neutrinos. So we know that active neutrinos exist. These are super, super light particles that are almost massless, but do have a small amount of mass we don't know, that we can't really can't really pinpoint. But it is whatever the mass is, it's very light. And people wonder like, why are neutrinos so different than the rest of the standard model? It's a very fair question. And so there's this mechanism called the seesaw mechanism, which very roughly says that you can actually give that mass that the active neutrino would have had to like a heavy counterpart. And this is why it's called a heavy, what's also called like a heavy neutrino. So these sterile neutrinos would pick up basically this mass through this mechanism, and they would be very heavy, and they could be a candidate for dark matter this way. It's called sterile because we don't observe them. They occupy a different representation in the standard model that isn't that is in the right-handed representation for those that know that the weak for those that know that the standard model is like chiral and that we only observe like left-handed type particles. That we haven't observed like the sterile neutrino, but it's definitely a thing that people think about and try to look for in like astrophysical data sets. Like here, there's a Chandra image of like the Perseus cluster, as well as up there, there's like a kind of a cartoon of like Dune, one of these experiments that tries to essentially look for like neutrino oscillations. And you might hope there could be signatures of sterile neutrinos in the neutrinos that they actually make. So this is kind of a little bit in the middle of the plot here, like in the KeV scale. So sterile neutrinos, yeah. They're definitely something that people think about, and kind of would be a nice extension of the standard model, kind of this right-handed component. And then the last exhibit that I'm going to show is a very popular one these days called the Axion. It's a hypothetical ultralight particle, which means it kind of lies on the far like left of this kind of mass plot on the bottom right here. I put the Axion cleaner there is because I think one of the stories of how the Axion name originated was because people who thought about the axions were like, well, it's a really nice particle that solves like this thing called the strong CP problem, which I'll mention in a sec. And it kind of wipes away, like problems in theoretical physics. And that's how they came up with the idea of calling it the axion. So the QCD axion, the quantum chromodynamics axion, which acts with a strong force, is the most well known. And actually, yeah, the reason why it was created was because people wanted to wipe away the strong CP problem. The strong CP problem is essentially a statement of like, why is CP, like charge parity, so strongly conserved in the strong force? Or another way of putting it is like, why do we not have a neutron electric dipole moment inside a neutron? So that's this bottom diagram here, where you have kind of a cartoon of like two down quarks and an up quark, which make up a neutron, for example. And the natural thought experiment is like, well, if I think about it, like the down quarks have like a charge, the up quarks have a charge. There's an overall charge, like dipole moment, in the same way that water has a dipole moment because they have two hydrogen and one oxygen, both which have different charges. And so there should be like some kind of electric dipole moment in like a neutron, but we don't observe this. And so people who came up with the axion were like, well, what if you had like this kind of invisible field of like very light particles that were present in your system that is able to essentially like manipulate the angles very roughly at which these quarks are situated, such that it can actually cancel out this electric dipole moment, and that's why you observe none. And so people, this particle would then be called the axion. And so people really love it because of this reason. It would solve this problem. It's a very beautiful, kind of way that it solves this problem. And for people who are fans of like string theory, for example, axions also pop up generically in string theory. So that's another reason why people think that axions might actually be a real particle that we can observe. And of course, for our purposes, the axion actually can be a dark matter candidate. So there are ways that axion can emerge that would produce a dark matter density today. And it'd be a very light particle, but it's definitely a candidate that is very motivated. Rhetorical question for myself: is the search for dark matter just beginning? I'm a graduate student that kind of works in this, so I hope the answer is yes. There's many motivated particle candidates for dark matter, and now I think kind of the big appeal is we can search for them with like 21st century data. And so everything that you see on this plot are things that people have started to extensively look for. And now I think isn't kind of an even more fun, kind of the last part of the talk, which is how do we actually go and look for these particles, right? Like, let's not have all these things just live in theory space. You actually want to see if you'd observed a particle or not, or if you actually have a chance to see if these particles are your candidate for are the actual dark matter candidate. So how do you look for them? Usually you just have to assume some connection to the standard model. For example, like if you believe in all of these other candidates, then you believe that this is generically true, that you should have some coupling, if not very weak, but it could be, but there's some non-zero coupling to things like electromagnetism, the weak force, the strong force, etc. Otherwise, you're never actually going to observe it besides gravity. But we think we have reason to believe that there are going to be connections to other types of standard model particles. And so with that, there's a lot of directions you can go. I like this diagram. This diagram kind of tells you the different ways in which people look for dark matter. So you can read it like you have normal matter stuff on the left, dark matter stuff on the right, and depending on the way that you read it, up or down, left or right, is kind of the way in which people try to look for a dark matter particle. So for example, the one that isn't really my specialty, but some people definitely have thought a lot about is called direct detection. That's just code word for I'm going to build an experiment here on Earth, and I'm going to hopefully directly detect a dark matter particle running through my experiment. So you read it a direction like from down to like bottom to up. So you have a dark matter particle and a normal matter particle. They hopefully like scatter off of each other into a dark matter particle and a normal matter particle. And so people who build these detectors like LZ or Xenon or something, which you may have heard of in the news, they basically they hope that a dark matter particle comes in, like scatters off of some nucleus, which then emits signatures of like light and other things that your detector would be able to detect. So this is what the direct detection dark matter person does. They got some pretty strong constraints for these too. Of course, there's other directions that people go into, like colliders, in which you basically put so much energy into normal matter particles that they're able to hopefully, in the shower of particles that comes up, produce a dark matter particle. And then the cosmologists basically can go both ways. You can have kind of like even a thermal equilibrium between the standard model particles and dark matter particles that come into and out of each other, that interact with each other in the early universe, and that produces signatures that you can observe later on, like today. And so here's like, for example, some diagrams of how you might actually do this. The collider people kind of, it's always the same. It's always the same idea, which is you collide for particles and you look for like missing momentum as like a missing particle that you don't know how to explain. The cosmologists can do these things in like observations of the early universe, like the CMB or something, or they can run simulations in which dark matter interacted with the early universe and then influenced the evolution later on. And so these are all really interesting things that people do and kind of searching for dark matter. The one that I really want to highlight in kind of the last piece of my talk is the astrophysical part, right? Because I always come back to this, that astrophysical evidence of dark matter should naturally lead one to wonder, there's probably astrophysical evidence of dark matter particles. And this is kind of the philosophy I subscribe to. So this is the thing that's called indirect detection. That's code name for essentially astrophysical probes of dark matter. So you read it from right to left, where you have dark matter somewhere in the universe that interacts with itself such that you basically produce normal matter that you hope to detect, like photons or like electrons or other things that are streaming throughout the galaxy. And this isn't, just isn't, this is a very reductionist like picture of like how a lot of these detection mechanisms work, but this is probably like kind of the biggest image people have in mind is like dark matter that is present in the universe going into standard model things that we hope to observe. I think astrophysics is very motivated. I think it's one of the most exciting methods because there's a lot of different environments that you can use to probe dark matter using astrophysics. For example, like stars, like you can't replicate the interior of it. It's very hard to replicate the interior of a star here on Earth with such high density, such high temperatures, for something like a neutron star or something like that is even more improbable. But fortunately, there are these things that exist out there in our universe. You can't really get the scale of things on a galaxy scale either, right? And so you want to take advantage of all these different environments. The other thing that's nice about indirect detection astrophysics is that you can access regions of very high dark matter density. So if you build a detector here on Earth, you're relying on the local dark matter density, which is much, much weaker than if you were to look at, for example, like the galactic center, where you expect a lot of dark matter to collect gravitationally over time. Kind of a follow-up to this is that you have increased sensitivity to very long-lived or weakly interacting particles because in astrophysics, you get to accumulate them over long times and long scales. And so if you have something that very rarely happens, of course, if you look at so many of them, you might find one in which it actually happens. And so, of course, the other thing that I like to say also is that dark matter was originally discovered from astrophysics in the first place. So I think it's really nice to kind of come back and say, well, how much more precise can we make this search for astrophysical dark matter? And here's like a splattering of essentially a lot of different astrophysical environments that people have looked at. All of these have been kind of stages where a lot of like physicists, a lot of especially like, people who started out in particle physics have now directed their attention to a lot of these astrophysical environments. And I've tried to look for, some of the candidates that I've mentioned before and how a dark matter signal could actually be produced from this and how you can go observe it with like a telescope. I'm going to do one case study before I finish, which is a little bit of an illustrative demonstration of kind of what I do, is that I look for axions. A lot of my work is looking for axions in stars. And so axions, again, are kind of this ultralight pseudoscalar particle that's very popular candidate for dark matter. And generically an axion-like particle, which is this A field here. By the way, what I'm showing is like the effective field theory Lagrangian for the axion, which are essentially just encoding like physics terms that the axion can possibly interact with. Which is just a fancy way of saying I'm going to just show how the axion might interact with all the other things I know of in the standard model. And some things that are included in this picture is, for example, the axion coupling to electromagnetism. So for those who are familiar with like quantum field theory or like Lagrangian mechanics, the F mu nu is like the field strength tensor for E and M. Which basically is like a representation of like the E and M field, which eventually gives rise to like photons and stuff like that. And the axion can generically couple to this. And it's measured by the axion photon coupling GA gamma gamma, which sets the interaction strength for this. Then you can also have axions coupling to matter on the right. So your F or F bar are like your fermions, which can be like electrons, for example, and you can have the axions generically coupled to electrons. But the thing I want to highlight is that these couplings can be magnified in extreme astrophysical environments. So while these couplings might be very small, like might have difficulty detecting these things in like an actual detector that you build on Earth, in an astrophysical environment, you can access much more extreme kind of areas in which these couplings can be magnified, and you might actually go out and detect them. And this is what I find pretty exciting about like stars, for example. So here's a kind of a more cartoon demonstration of kind of the things people look for axions. One very classic example is this mechanism of stellar cooling. So you can have axions that are produced inside a star through these couplings that I just mentioned. And then these axions are so light and so weakly interacting that they free stream out of the star and they carry energy away. So then that affects actually how the star cools and the evolution of the star itself, right? If you suddenly have a source where that is inside a star that is taking away energy, then all your conditions of like hydrostatic equilibrium have to change. And so this would affect different stages of a star's evolution that you can observe. You can also look a little closer at like how the axions are actually produced in the star. So you can have there's a variety of processes where you can have axions that are produced off of interactions with the photons, off of interaction with electrons, other particles. And then these types of axions, when they free stream out of the star, can convert back into a photon. They can convert back into a photon, and it might be a photon that you actually can detect. They can convert back into a photon because of its coupling to the E&M field and because you're in like some kind of magnetic field environment. Whether this magnetic field is like your magnetosphere of the star, the magnetic field of the galaxy that you're in, or if you built a detector and you apply a magnetic field in your detector, an axion can come in and then if it has a coupling to E&M, then it will have some probability of converting into a photon. So let me like rearrange this a little topologically. In the form of something that's more commonly known as like a light shining through wall experiment, but this is the astrophysical version. You produce an axion from the interaction of like stellar plasma. In like some magnetic field, whether this is the magnetic field of a galaxy, the star, or like an experiment on Earth, this axion can convert into a photon, represented by the gammas, by the way, I forgot to mention, and become light. And this light that you hope can then be detected by like a telescope, for example, or like your detector on Earth. And so this usually leaves like a very conspicuous signature, a very unique signature of axion production in the kind of the X-rays or gamma rays that you see. And so this would kind of be a signature of like an axion particle being produced in stars if you're actually able to observe it. And this is a lot of the work I do, for example. Haven't really found axions yet, but with better like telescopes in the future, better experiments, better like kind of astrophysical understanding of like systematics that occur inside a star, because it's not like we live in a star, so we have to make some assumptions. We can like kind of look in other similar directions, or like just look a lot more closely if the couplings, for example, are a lot weaker than we think they are. There's many other things that you can look for. For example, people have looked at these types of processes in like the sun. They call it helioseismology. There's like an experiment at CERN called CASS, which looks for axions from the sun. They set up their own magnetic B field there. So helioseismology is like how does the axion cooling affect like the sun's like temperature, like sound profile speeds, sound speed profiles. People have looked at other stars, like I've looked at, for example, like white dwarf stars, and then you can look at like more extreme stars, like supergiant stars. People have looked at like clusters and collections of stars. So you can look at, for example, there's these funny collection of stars in the sky that are known as like globular clusters. These are very old, very homogeneous populations of stars. But the axions, like if they any deviation from kind of this known understanding of globular clusters could be a sign of axion emission. And actually, there are some anomalies in a lot of these types of astrophysical observations that people think could be explained by like axions being produced in these stars and then causing some kind of like energy imbalance that would explain like the anomalous evolution of a lot of these types of systems. A lot of some other people, including myself, have looked at, for example, galaxy populations, where how does the axions produce in like a stellar population show up like as a signal that you might be able to detect with like a local telescope. Many ideas abound, a very non-exhaustive list. I barely scratched the surface, but I'm generally very excited about like where astrophysics is going to take us in the discovery of dark matter. Um, there's a lot of very exciting things being proposed in the gamma ray, X-ray, radio bands, objects as diverse as the galactic center, compact objects like neutron stars and white dwarfs, like even like blank regions of the sky in the galactic halo, and all the different types of dark matter candidates that you could probe. And so I find this like a very fun field to kind of go into and explore. I think, with new telescopes are being proposed, more time is being given for these telescopes, a flood of data is coming in. I think there really is opportunity to really discover what the dark matter particle could be. And here's just kind of a status on like two examples of things that people look for in the dark matter search. On the left is like from the LZ collaboration, which is one of the direct detection experiments, where they basically look for like WIMPs, weakly interacting massive particles, come in and scatter off of their nuclei with some characteristic characteristic cross section, sorry. And they haven't observed any WIMPs, but their bounds are increasingly more stringent, which means that if a WIMP were to actually exist, its cross-section interaction with normal particles must be extremely small by this point. But you never really know until like you actually go and observe it, right? Because WIMPs are still a very, very popular, like theoretically motivated candidate. But that doesn't mean nature has to give you WIMPs. But you'll never know until you observe it. So same thing with this axion story on the right, where you kind of look at the axion mass as a function, the coupling of the axion photon parameter as a function of axion mass. And all this white space basically just means regions we haven't explored, which means the axion could still exist with that mass and that like weak coupling, which is all the white space that people are trying to get into. I just want to say that astrophysics, for example, give many of the strongest constraints on this plot for axions. So astrophysics is incredibly useful in trying to tease out essentially very weak. So if I go back here, right, like notice how the coupling gets weaker and weaker the bottom down you go. But the astrophysics are able to kind of probe some of the weakest couplings. None of these have really found axions. So that means the axion coupling, if the axion really exists, must be weaker than all of these current probes. And this is kind of the game that we all play. But a lot of people still believe in these models, and I think they're still very well motivated. So we keep looking for them in the hopes that, with more telescope data to cut out large swaths of the state of this space, or like more detector data, or like novel ideas in both of these fields, you could conclusively discover or rule out these types of particle candidates. My very brief summary. So dark matter is kind of one of the very few problems in theoretical physics that we know a lot about, despite not really knowing. And I think it's very special, right? There's a lot of problems in theoretical physics, but none are really quite as tangible, in my opinion, as like the dark matter problem. We know it has to exist from astrophysics. And we have a lot of very motivated candidates that now we're able to probe in our golden age of like data, which is totally unheard of, for example, for a theorist in like the 70s or 80s or so. It's a problem across multiple branches of physics. So this kind of journey has taken me all throughout like particle physics and astronomy and like data science and all sorts of different types of branches of science at the smallest and highest scales. And it would be really a generational defining moment, I think, if we were to finally solve it and determine what dark matter particle is once and for all. All right, thank you. So all I'm going to say is that the truth is out there. I think there's a lot to be excited about in terms of these dark matter candidates, because it's still a very real problem that we don't know how to explain. And so only time will tell what we actually discover within the next decade or so. Thank you.
Thanks so much for a great overview of the state of the field.
Yeah. Thank you.
We'll see if there are any questions on the chat.
Yeah.
But maybe I'll start.
Is the recording stopped?
The recordings should still be going.
Okay.
Yeah.
Okay. Yeah.
I just have one real quick, which I don't know how specific you can be without like figures and pictures, but
yes.
What are some of those signatures of, for example, axion?
Yeah, that's a good question. So for example, if we were to look at like a light shining through walls experiment, which I kind of mentioned. Oh yeah. So the question was, like what would an actual like signature look like, for example, from like an axion search in like astrophysics? Like what would you actually look for in a telescope? So if kind of a lot of the work I do, for example, when you look at like axions that are being produced inside a stellar interior, like in this diagram here, this axion, the photons that cause the axion production are going to be thermally produced inside the star. And so they're going to kind of align with the temperature of the star inside. So for example, like the sun would have a temperature of like a keV. which is some Kelvin, but let's you know, I'm used to like natural units, so like it's going to be like some keV, which means that kind of the axions that are produced and then convert back into photons will also be around the scale of a keV. So you're going to be looking for like a peak in keV, like X-ray spectrum in this type of search. If you go to like a supermassive, like a supergiant star, you would more have like 30 keV. So you're going to start to see a lot of axion, like you'll see X-rays that kind of peak around 30 keV. They'll be a very conspicuous spectrum in like a kind of like an X-ray like observation of like a star. Of these types of star. If you look at like a sterile neutrino model, the sterile neutrino is kind of special. The sterile neutrino decays at a very precise line of you know, like so one very motivated one that people always look for is like 3.5 keV. So in that case, you're looking for like a smoking gun line signature from like a sterile neutrino decay that comes from a very specific particle decay process. And so those are like kind of the things you can look for. Other types of processes give you gamma rays. Other types of processes like synchrotron radiation for like WIMPs and stuff can give you like radio signatures, but they all appear as basically, you know, usually like some kind of spectral shape. Or if you're looking at like how stellar cooling affects the can give you a signature for like axions and stuff like that, like here where the axion takes away energy. You're not observing the axion itself, but you're looking at a star and you're kind of like looking at a collection of stars and saying, at what point does this, like statistically, this collection of stars start becoming like a red giant, for example? Because if it's earlier than expected, this could be a sign of axions taking away more energy that you cannot explain through your normal astrophysical model. So that then you'll be looking at like these types of stars and from telescopes. Yeah.
We have one question to that.
Yeah.
Alex asks, can you briefly elaborate on what you meant by the standard model being chiral and observing left-handed particles?
Oh yeah, that's a great question. So our theory of the standard model, sorry, I can go back here. Our theory of like the standard model is essentially like if we were to go in kind of detail, the standard model is dictated by a bunch of symmetries. The symmetries being like an SU3 color, cross like SU2L, cross like U1 hypercharge group. If those words don't mean anything to you, that's okay. Basically, the idea is that like there are these symmetries that give rise to the collection of particles and their types of interactions with each other. So the statement that I was making before is that like things that interact weakly with the standard model are left-handed particles. So you can very briefly like think of like chirality is like a property of a particle. So some particles are naturally left-handed, some particles are naturally right-handed. In the massless limit, so like for a neutrino, if they were actually massless, this would be the same thing as helicity. So a neutrino will come in, right, and they would like be spinning in one way, in the direction of its motion. And like a neutrino, a right-handed, like if a left-handed neutrino did that, the right-handed one would be spinning the other way. And so this is in the massless limit, helicity and chirality are kind of the same thing, and they can kind of be visualized like the actual like spin of a particle as it's like as it has momentum going toward a particular direction. And so some particles are naturally left, some particles are naturally right. These quarks, for example, they have there's like left-handed quarks as well as right-handed quarks exist, although only the left-handed ones interact with the standard model through the weak interaction, because the weak interaction is only differentiates between the left and right-handed parts, and the weak interaction only cares actually about left-handed particles. I didn't make that up, the person who made up the entire nature, the theory of nature that we have today, has basically found that this is true for some strange reason, that only like left-handed particles interact with the weak force. And so these neutrinos, we've never observed a right-handed neutrino ever in our life. So we've only observed like these left-handed neutrinos, which again, like they kind of, you can think of as they're kind of spinning in a certain way in their direction of momentum. We've never observed the opposite happen. And so I guess the question, which is kind of expanding a little bit more about like, what does it mean for the standard model to be like chiral? It basically means a part of the standard model, the weak force, right, differentiates between a left and a right-handed particle. They're not treated the same. And for some reason, we see a lot more like left-handed interactions than we do with like right-handed interactions, and we don't know why. Is another kind of open problem. Sorry, did that answer the question for whoever was in the chat?
Yeah.
Yeah. Okay, great. Yeah. That is a very good question. It's a very like a deep theory too. There's a lot to say about it. Yeah.